So let's look at magnetic field due to what? When we have a solenoid and a toroid. Okay, a solenoid is actually some loop of wire in this manner, but a toroid is a solenoid wrapped in form of a donut. All right, now let's look at the magnetic field. And there's something I want to tell us. For a solenoid, the magnetic field is very strong at the center compared to the outside. Now, let me consider this as our loop of interest. Let me consider this as our loop of interest. So let me call this point A, B, C, and D, for example. And according to Ampere's law, we have this integral B dl equal mu naught I what I enclosed. Now, one thing is that remember that if I evaluate this dot product, check it out. You observe that for me to cancel this dot product away, this B and this DL must be parallel in the same direction. My magnetic field is at this direction here. This is my magnetic field at this direction, B. But the thing is that what I want to tell you something. The DL we are going to make use of must be the one that is parallel to this magnetic field. Are we together? Observe. If you pick the one that is perpendicular, it will not work. Remember that what the dot product of two vectors, if they are perpendicular, the dot product is 0. So it means that what I will only pick the magnetic field at this point only. I will only pick the one at what BC. Do you know why? That BC is along the same direction with the what magnetic field. But if I choose CD, look at this one. This CD is actually what perpendicular, and this will give me 0. Also, this is what perpendicular, this will give me 0. But observe, this one is also in the same direction. But I will not still pick AD because AD is outside this solenoid. Remember my first word, I said that what the magnetic field outside a solenoid is very small. Are you there? So it will be what? Negligible. Are we together? So it means that what I'm actually picking here for this what? For this solenoid is what? Is BL. Are we together? That is what the length. Just BL. I can't pick this, I can't pick this, I can't pick this. Okay? Because this and this are perpendicular. Why this one is outside the solenoid and it will what? It will be very weak. And that's equal to what? Mu naught times what? Times the current what? Enclosed inside this what? Solenoid. Now from here, what will I do? And what is this current enclosed? Just tell me, what is this current enclosed? Now, assuming I have a loop, let me assume this loop is 10 ampere. Now, if I have two loops like this, I'll have 20 ampere. If I have three loops, I'll have what? 30 what? Ampere. Are we together? So it means that what this current enclosed will be equal to what? The number of turns times the current. Are we together? Ni, depending on the number of turns. So I'll have a BL equal mu naught Ni. So from here, I'll have the magnetic field equals to what? Mu naught Ni divided by what? The length of the solenoid. Now, what is this number of turns divided by length? You see, this number of turns divided by length, we call it what? The turns per unit length, and that is what? I can replace it as small letter n. So the magnetic field for this solenoid using Ampere's law is what? Mu naught Ni, and that is it. This is for a what? This is for a solenoid. This is for a solenoid. Now, for a toroid, remember, a toroid is a solenoid wrapped in form of a donut, and this is it here. Now, how do we go about this one? Remember that what? The distance that will be covered by this L will actually be the area of the circle when we are considering what? A toroid. So here we are having B times what? 2 pi r. And that will be equal to what? Mu naught I. And remember that what? The I enclosed here also. The I enclosed there will also depend on the number of what? Of turns. So I have what? N I. So I have B times 2 pi r equal to what? Mu naught. Then I enclosed, mu naught I enclosed times N, number of turns, no problem. So from here, what will I do? I'll have the magnetic field should be equal to what? Mu naught Ni all over what? 2 pi r. This is when you are dealing with what? A toroid. You can see that what? It's very simple. For a solenoid, we are having what? L. which is the length. While for a toroid, instead of us having the length, we are having the circumference of the what? Of the circular part, and that is what? 2 pi r. Your n is the number of turns. So that's the magnetic field due to a solenoid and a toroid. All right.